I'm happy to be here to present our paper, SAGE. This is a framework aimed at language-guided generalizable articulated object manipulation. Articulated object manipulation can be very challenging due to the diverse semantics, geometry, and actions of articulated objects. Today's topic is semantics reasoning and goal understanding. So how can we actually understand the semantics and the action goals in such challenging tasks? As we all know, general purpose large models have a rich semantic understanding, while domain specialist robotic model can understand physics and actions better. So in our proposed model, we hope to mix their strengths together to balance semantics and physics. Imagine that you bought a new blender to your kitchen. To make juice with it, you need to truly understand the semantics and the functionalities of its parts, in this case, the container. To turn on this blender, the robot needs to press its container and it will blend the ingredients in it. And here, we understand the part at semantics level as a container, just like the container in the coffee machine. It was used to load ingredients. But when we want to turn on it, we consider the part at the action level as a part to be pressed, just like a button. So here, we introduce our SAGE framework to understand part at both semantics and action levels. Our pipelines take human instructions as input and interpret it into a semantic part and action program. The action program is a triplet of semantic name, join type, and state change. So to achieve so, we first make our domain specialist model GAPRNet and the general purpose large vision language model GPT-4V to generate a context-aware scene description. The scene description, along with the human language instruction and the optional user manual of the object are joint embedded into a template prompt and are then input to GPT-4V to generate semantic part names and action programs. And here, we further ground the semantic part into the target actionable part. Here, for the blender, the semantic part is a container, and the actionable part is a slider button. We then estimate the part pose along with the pressed motion. And finally, we execute the action and turn on the blender successfully. So here is another very interesting task. The instruction is to open it without the object name. And the same as before, we first generate a context-aware scene description, and then semantic part and action programs. And with our grounding model, we then get the actionable part post and the joint. But interesting happened. Attempts to open the door by utilizing the handle will it's closed, failed. This is because the microwave cannot be opened by directly using the door, but need to use the button to open it. So here, give the feedback on feedback on the large part post and the target part post and the actual part post to our planning model GPT-4V, and it finds some failure and decide to reply. And this time, with prior knowledge and part analysis, GPT-4V says that pressing the button on the to open the door slightly and followed by an action to revolve the door. And you can see here the new policy executes successfully. And our proposed model can handle very diverse and even vague instructions and have a very strong generalization abilities. And here I show several interesting demos here, and you can see our model can handle like even diverse and even vague instructions and have a very strong generalization ability. And like in this talk, I show a lot of demos and intermediate results. But if you want to know more about how we actually combine the 3D models and the 2D models together, please visit our poster or check our paper.